Hello everyone, welcome to EnviroPioneers. In this video, we will discuss the fundamentals of wind formation in the atmosphere. In our previous video, we discussed the atmospheric pressure in detail, including how it forms, how it varies with the altitude, and why warm and cold air columns behave differently. So, based on what we understood in the previous video, we will take a step further to understand how these pressure variations cause the air to flow. This video will explain how atmospheric pressure produces wind and examine the main factors influencing the wind speed and direction. As atmospheric pressure varies with the altitude, to maintain the consistency, the atmospheric pressure is reported as standard sea level pressure, which represents the average pressure of the Earth's atmosphere at sea level under standard conditions, which is defined as a temperature of 15 degrees Celsius. So, here we have the standard sea level pressure in different units, and these we have discussed in detail in the last video. If we use mercury barometer to measure the atmospheric pressure, under average sea level conditions, the atmosphere exerts enough pressure to push a column of mercury up to the height of 29.92 inches or 760 mm. Thus, sea level pressure is reported as 760 mm or 29.92 inches of mercury. There are different units in which sea level pressure can be reported, but meteorologists use millibars as the units of measurement for the air pressure, and the standard pressure at sea level is 1013.25 in both millibars and hectopascal. And this value 1013.25 millibars serves as the division between high pressure and low pressure at the earth surface. Means at any location, if the value of atmospheric pressure is more than 1013.25 millibar, it is referred as the high pressure, and if the value of atmospheric pressure is less than 1013.25 millibar, it is referred as the low pressure. Air pressure or the atmospheric pressure decreases as we move up in the atmosphere, and this rate of change is similar to the change in the air density. As shown here, lower in the atmosphere, the molecules are very closely packed together. Thus, here near the surface, air is having the higher density. But as we move up in the atmosphere, these molecules are spread far apart and air is less dense. So here we can see the air density also decreases as we move up in the atmosphere. Thus, rate of change in the atmospheric pressure with altitude is more near to the Earth's surface, but it is less when we move up in the atmosphere. So, here it is mentioned that the air pressure decreases more rapidly between two elevations close to the surface than between 2 points separated by the same distance aloft. As we can see, from 0 to 50 km near the Earth's surface, the pressure changes this much. But higher in the altitude, for example, from 250 to 300 km, the pressure change for these 50 kilometers is much less in comparison to the 50 kilometer near the Earth's surface. And as we use an average value of sea level pressure to differentiate between high pressure and low pressure on the Earth's surface to analyze the conditions aloft, that is, up in the atmosphere, the 500 millibar level is used as the standard pressure level in the meteorology. This value is chosen as the standard pressure level because 500 millibar is considered as the middle of the atmosphere, with roughly half of the atmosphere's mass below it and half above it. And this pressure level generally occurs at an altitude of approximately 5600 meter, that is about 18,000 feet above the sea level, but its exact height varies with the temperature of the atmosphere. Measurements of the parameters like the temperature, pressure, or humidity in the upper atmosphere is done by using the radio sondes, which is placed on the weather balloons. As these weather balloons rise upward from the earth, They continuously monitor and record the data for different parameters, and it is continuously sent to the ground stations. So, from the data collected from the upper atmosphere, it has been observed that at the altitude of 5600 meter from the Earth's surface, the average pressure is 500 millibar. So, if on any given day the pressure is larger than 500 millibar, we consider it as high pressure at the altitude of 5600 meter, and if it is less than 500 millibar, then it is low pressure at this elevation. So in meteorology, the high pressure and low pressure is used both at the surface and in the upper atmosphere. At the surface, standard pressure at sea level, that is 1013.25 millibar, is used as the reference. Means if the value of atmospheric pressure is more than 1013.25 millibar, it is reported as high pressure, and if it is less than 1013.25 millibar, it is reported as low pressure. And above in the atmosphere, 500 millibar level is used as the standard pressure level. Means at that particular altitude, if the value of atmospheric pressure is less than 500 millibar, it is low pressure, but if it is more than 500 millibar, it is high pressure. Meteorologists have a variety of ways to visualize the weather data, in which map is the most common. So, pressure variation map is represented in two ways: horizontal pressure variation at the surface and horizontal pressure variation aloft, means above in the atmosphere. Horizontal pressure variation at the surface means the variation of the atmospheric pressure at the Earth's surface, and it is represented in the form of surface chart. As pressure decreases with altitude, the values of atmospheric pressure observed at different stations will vary depending upon their elevation above the sea level. Thus, for preparing the surface charts or to show the horizontal pressure variation at the surface, the observed value of atmospheric pressure is calibrated and corrected using sea level as the common baseline. Thus, on all the surface charts, the elevation of the surface is considered as 0 feet. Maps prepared from the corrected and the calibrated value of the atmospheric pressure is referred as the constant height map or constant height chart, and these show the distribution of pressure at the sea level. And the isobars, that are the lines connecting the points of equal pressure, are used to show the pressure patterns on the constant height maps. As decrease in atmospheric pressure is observed with the altitude, the pressure patterns are also analyzed for the upper atmosphere, and it is represented through the constant pressure map, which is also known as the constant pressure chart, and these give the horizontal pressure variation aloft, that is horizontal pressure variation up in the atmosphere. These constant pressure map show the change in the elevation of an isobaric surface, that is also known as the constant pressure surface. So this is a surface upon which the pressure is the same at all location. And for the purpose of weather forecasting, 500 millibar surface is commonly used by the meteorologist. The 500 millibar surface is a constant pressure surface approximately midway in the troposphere, where the pressure exerted by the air column above this level is exactly 500 millibar. The normal height of this 500 millibar surface is approximately 5600 meter, but this height may vary from roughly 4700 meter in the extreme cold atmosphere to approximately 6000 meter in the warm atmosphere. In this image, three air columns are shown to explain the effect of temperature on the atmospheric pressure. In the center, we have a standard column which represent the atmosphere in the standard condition, means the temperature is about 15 degrees Celsius. So in the standard condition, this is the height for the 500 millibar surface. On the right hand side, we have a column where the temperature is much colder. When temperature is less, means in the colder condition, due to the slow movement of the molecules, most of the molecules are concentrated near the surface and air density decreases rapidly with height. So, as there are very less number of molecules present in the upper atmosphere, pressure decreases rapidly with height. But in those areas where the temperature of the atmosphere increases because of the heating from the Earth's surface, the molecules spread out, and if we consider an air column, it would contain significant mass even at the higher level. And in this condition, pressure decreases slowly with height. Though these three air columns may exert the same amount of atmospheric pressure at the ground, but the rate of pressure change with altitude varies depending upon the temperature of the atmosphere. If we consider a particular altitude up in the atmosphere, so depending upon the amount of air molecules present above that altitude, atmospheric pressure will vary. For the warmer air column, because of the spreading of these molecules, more number of molecules are present above this altitude. So here we have the atmospheric pressure of 500 millibar. But for the same altitude in the colder air column, as there are less number of molecules present above this altitude, the atmospheric pressure is less than 500 millibar, and the same value of atmospheric pressure is present at the lower altitude. So, for the same height, the atmospheric pressure in the warmer air column will always be more than the atmospheric pressure in the colder air column. Using the constant pressure chart, thickness contours are also prepared. Thickness is the measurement of the distance in meters between any two constant pressure surfaces. And one of the most common thickness charts that is used in the meteorology is the 1000 minus 500 millibar thickness. So here we can see near to the Earth surface we have the 1000 millibar constant pressure level, and up in the atmosphere we have the 500 millibar height level, and the difference in between these two is the thickness, that is the difference in height between the 1000 millibar and 500 millibar levels. Thickness between two constant pressure level varies with the temperature of the atmosphere. In the cold air, as the molecules are concentrated near the surface, the change in atmospheric pressure from 1000 millibar to 500 millibar occurs at the lower altitude. So, in cold air, the thickness between 1000 millibar and 500 millibar is small. But in the warmer air, as the molecules spread apart, the rate of decrease in the atmospheric pressure is less. So here we can see for decrease of atmospheric pressure from 1000 millibar to 500 millibar requires greater thickness. So here it is mentioned that higher temperature leads to greater thickness for the same pressure drop. So for any constant pressure level, the pressure surfaces lie at higher altitude in the warm air and at the lower altitudes in the cold air. Now, with this concept, let us understand a scenario where we have the column with warm air in the left while the cold air in the right. And this white surface is representing the 500 millibar surface. And let us assume that the atmospheric pressure at the surface is constant. So, when air is heated, it becomes buoyant and it rises up in the atmosphere, while in the colder condition it sinks towards the surface. In standard condition, this 500 millibar surface is present at the altitude of 5600 meter. But when the temperature is high, as the warm air rises, more air molecules will be found above this 5600 meter than normal condition. Thus, the 500 millibar surface is found at the higher elevation. But when the temperature of the atmosphere is less, cold air it sinks near the surface, and very less number of molecules are present above 5600 meter, and it is less than the normal condition. Thus, the 500 millibar surface is found at the lower elevation. So in this scenario, we can see the constant pressure level of 500 millibar dipping from left to right because the temperature on the left hand side is warmer and temperature on the right hand side is colder. Now, if we consider the altitude of 5600 meter in the atmosphere, so where we have the warm air, more number of molecules are present above this altitude. So here, this particular altitude is at high pressure. But in the colder region, less number of air molecules are present above the altitude of 5600 meter. Thus, in this region, this particular altitude is having the low pressure. By worldwide convention, constant pressure charts are typically created for 200 millibar, 300 millibar, 500 millibar, 700 millibar, and 800 millibar pressure levels. Together, these five levels give the meteorologist a good representation of the state of the atmosphere. And on any given constant pressure chart, the air pressure is same at all locations, and only thing that varies is the altitude where that particular pressure occurs. As atmospheric pressure varies with the temperature, the altitude where any particular pressure occurs will be lower in the regions of the colder air and higher in the regions of warmer air. And this is the reason, as a rule, the altitude of constant pressure levels decrease from the equator towards the pole because it is warmer at the equator than at the poles. As altitude for particular pressure varies with the temperature of the atmosphere, lines are drawn on the constant pressure maps to represent the altitude at which that particular pressure occurred. And these lines are referred as the isoheights. So these are the lines of equal geopotential heights, and these represent the altitude of constant pressure level. These geopotential heights are different from the normal height above the ground because geopotential heights refer to the height of a point above the Earth's surface measured from the mean sea level, which is adjusted for gravity's variation with altitude and latitude. So, in the constant pressure map, the areas having lower heights, these are called troughs, and they represent colder, more dense air, while the region having the higher heights are called ridges, and these represent warmer and less dense air. So, in the upper air map for the atmospheric pressure, these isoheight lines are referred as the contours, and in the map, trough appear as dips or dashed lines, while the ridges appear as bulges or zigzag lines. These ridges and troughs in the upper air contours are related with the weather phenomena on the ground because troughs bring unsettled, cool, and wet conditions on the surface. Because if you notice here, trough is followed by the zone of divergence. So, up in the atmosphere, if we are having the zone of divergence, it means on the ground we will be having the region of low pressure, and because of the low pressure on the ground, the air mass will converge at this point and it will rise upside. And due to rise of air mass at this particular location, there will be cloud formation and precipitation. Thus, here we have the cool and wet condition. And if we note here, ridges are followed by the zone of convergence. So here the air mass will subside towards the earth surface. So at the earth surface, here we have the region of high pressure. And as air subside, it will become warm. So here it is mentioned, it brings warm, fair and dry weather. Now, as we have understood the concept of atmospheric pressure, let us learn how the horizontal variation of atmospheric pressure is related with the wind. In our previous videos, where we learned about the lapse rate and atmospheric stability, we discussed the upward movement of air and its importance in the cloud formation. Though the vertical motion of air mass is important, far more air is involved in the horizontal movement, the phenomena we call as wind. In one of the video in this playlist, we covered a topic, processes that lift air, where we discussed about the factors that are responsible for vertical movement of air. So now let us understand what causes the air to move horizontally. Wind is the result of horizontal differences in air pressure, and air flows from areas of higher pressure to areas of lower pressure. And these differences in the atmospheric pressure is mainly because of unequal heating of the Earth's surface. Thus, solar radiation is the ultimate energy source for most of the wind. Wind is controlled by a combination of forces, including the pressure gradient force, the Coriolis force, and the friction. So, now we will learn about each of these factors in detail, and we will start with the pressure gradient force. To get anything to accelerate or to change its velocity, it requires an unbalanced force in one direction, and the force that generates wind results from the horizontal pressure differences. When air is subjected to higher pressure on one side than on other, the imbalance produces a force that is directed from the region of high pressure towards the region of lower pressure, and thus the pressure differences cause the wind to blow. The greater is the pressure difference, the greater is the wind speed. As we can see here, the steep pressure gradient is related with the high wind speed, while the shallow pressure gradient is related with the low wind speed. So, the term pressure gradient refers to the rate at which pressure changes with distance, and the pressure gradient force is the force applied on an air parcel due to pressure difference. On the surface charts of the atmospheric pressure, the spacing between isobars indicate the amount of pressure change occurring over a given distance, and it is related to pressure gradient. So wherever we have the closely spaced isobars, these indicate a steep pressure gradient and strong winds, and widely spaced isobars indicate a weak pressure gradient and light winds. It would be more clear from this image. Here it is showing shallow pressure gradient. For this much distance, the change in atmospheric pressure is from 1020 to 1012 millibar. So it is approximately 8 millibar. While if we see in this part, the change in atmospheric pressure for the same distance is from 1020 to 1004 millibar. So this is approximately 16 millibar. So here we have the steep pressure gradient, and it is responsible for high wind speed, while here we have shallow pressure gradient, and this is responsible for low wind speed. On a surface weather map, the pressure gradient force is always perpendicular to the isobars, and it points from high to low pressure. In the map, closely spaced isobars indicate stronger pressure gradient force, while the widely spaced isobars represent weaker pressure gradient force. Pressure differences observed on the daily weather map result from complex factors, but the most underlying cause of these differences is simply unequal heating of the Earth's land and sea surface. Now we will learn about the pressure gradient force in two parts. First is horizontal pressure gradient, which is related with the wind, and second is vertical pressure gradient, that is related with the hydrostatic equilibrium. So we will start with the first part, that is horizontal pressure gradient and its relation with the wind. To learn about this, we will take an example of sea breeze to understand how the temperature differences can generate a horizontal pressure gradient and thereby winds. In this image, here we have the vertical cross section of a coastal location just before sunrise. And at this time, we are assuming that temperature and pressures do not vary horizontally at any level. And this assumption is shown by the horizontal pressure surfaces that indicate the equal pressure at equal height. We can say here we have the zero horizontal pressure gradient, And as there is no horizontal variation in pressure, there is no wind. Now, here is the condition of the same place shortly after sunrise. So, as the sun rises, the unequal heating of the land and water creates a horizontal pressure gradient. As we have discussed in the video of temperature, that land heats more rapidly and to higher temperature than water, and it also cools more rapidly and to lower temperature than water. Thus, variations in air temperatures are much greater over land than over water. So, after sunrise, the land gets heated more in comparison to water. And as air over the land warms, it expands and it causes the reduction in density. And as we discussed in the initial part of this video, that as the temperature of the atmosphere is high, the same pressure level is present at the higher altitude. Thus, in this condition, we have the constant pressure surfaces which are bent upward over the land. So, this unequal heating of the land and water does not change the atmospheric pressure over the surface, but it results in the change in atmospheric pressure up in the altitude. As above in the atmosphere, the pressure surface become elevated over the land compared to over the ocean. So for a particular altitude, the atmosphere will be having high pressure over the land and low pressure over the ocean. So this resultant pressure gradient above in the atmosphere causes the air to move from the region of high pressure to region of low pressure, that is from the land towards the ocean. When air flows from the region of high pressure to region of low pressure, two things happen. First, as the air piles up in this region, the air density increases and it creates a surface high pressure over the ocean. Second, as the air flows from this altitude towards the ocean, the air density over the land decreases. So it creates a surface low pressure area over the land. So the airflow, which started in the upper atmosphere, generates a horizontal pressure gradient near the surface and it develops surface circulation where the air flows from the sea towards the land, and this is referred as the sea breeze. Here, a simple thermal circulation develops with a seaward flow above in the atmosphere and landward flow at the surface, and this circulation gets completed with the vertical movement of the air mass. Here we have the complete representation of the sea breeze. During the day, due to unequal heating of the land and water, region of high pressure and region of low pressure develops up in the atmosphere, which is responsible for generating the region of high pressure and region of low pressure at the surface. And then we have the complete atmospheric circulation. We saw the horizontal pressure gradient formed during the day and formation of sea breeze as the result. Opposite happens during the night because in the night the land gets more cooler in comparison to water. So over the ocean the temperature of the air mass is more. Thus the region of high pressure generates over the ocean and region of low pressure generates over the land. So we have the flow of air mass from the ocean towards the land in the upper atmosphere. And this airflow results in the formation of high pressure over the land and formation of low pressure over the ocean surface. Thus, a horizontal pressure gradient is generated, resulting in the airflow from region of high pressure to region of low pressure. So during night, there is seaward flow near the surface and landward flow above in the atmosphere. An important relationship exists between the pressure and temperature. So, the temperature variations create pressure differences and it results in the formation of wind. So, greater these temperature differences, the stronger is the horizontal pressure gradient and resultant wind. Daily temperature differences and the pressure gradient generated because of the temperature difference, as we discussed in the example of sea breeze, are generally confined to a zone that is only a few kilometers thick. But on the global scale, Variations in the amount of solar radiation received due to variations in sun angle with latitude generate the much larger pressure systems, which in turn produces the planetary atmospheric circulation. And once the pressure gradient force starts the air in motion, the Coriolis force, friction, and other forces come into play. Though the Coriolis force and friction cannot generate wind, but they greatly modify the airflow, and by doing so, these forces help to sustain and even enhance the development of the Earth's pressure system. Now, coming to the second part within the pressure gradient force, that is vertical pressure gradient. So, as we know that air pressure is highest near the earth surface and it gets progressively lower as we move upward through the atmosphere. So, there is vertical pressure gradient force. And we also learned that airflow is from the areas of higher pressure to areas of lower pressure. So, having these concepts in mind, we may have questioned why air does not rapidly accelerate upward and escape into space. It would have been possible in absence of the gravitational force, but this does not happen because of the force of gravity, which acts in the opposite direction to the upward directed vertical pressure gradient. So, there is an important balance which is usually maintained between these two opposing forces, that is vertical pressure gradient force that is in upward direction and the gravitational force that is towards the earth surface, and the balance between these two forces is referred as hydrostatic equilibrium. So in general, the atmosphere is in or near hydrostatic balance. In those conditions, when the gravitational force is slightly more than the vertical pressure gradient force, slow movement of air mass occurs in the downward direction. This type of downward air flow occurs, for example, within a dense Arctic air mass where cold air is subsiding and spreading out at the surface. Depending upon these two forces, there may be downward or upward motion of the air mass, and most of the large scale downward or upward motions are slow, having the average speed of few centimeters per second, that is less than 1 mile per day. But some smaller scale vertical motions are much more rapid. For example, strong updraft and downdraft associated with severe thunderstorms can reach up to 100 kilometers per hour or more, that is about 62 miles per hour. But these type of phenomena are sporadic and localized. Overall, the state of the atmosphere is in hydrostatic equilibrium where the upward pressure gradient force is balanced by the downward force of gravity. Here we have the summary for the pressure gradient force. We saw that pressure gradient force can be horizontal or vertical. So the horizontal pressure gradient is the driving force of wind. It has both magnitude and direction. Its magnitude is determined from the spacing of isobars, and the direction of force is always from the areas of higher pressure to areas of lower pressure, and the horizontal pressure gradient is always at the right angles to the isobars, while the vertical pressure gradient is usually in or near balance with the gravity, and this is referred as the hydrostatic equilibrium. Thus, upward and downward flow in the atmosphere is comparatively slow, with the exception of localized updraft and downdrafts. Now, coming to second important factor affecting wind, that is Coriolis force. Here we have one weather map which shows the typical air movement associated with surface high and low pressure system. This map we already saw while discussing about the pressure gradient and isobars. If you note, in this surface map for the atmospheric pressure, apart from the information about the region of low pressure and high pressure and isobars, there is one more information that is shown by using these symbols. So these symbols are referred as wind barbs. These wind barbs on the isobar map show wind direction, means from where the wind is blowing, and the speed of wind at a specific point. So here we have the legend for the isobar map, where against each symbol we have the wind speed in miles per hour. So from this legend we can extract the information about the wind speed. For example, this symbol, it represents the wind speed in 3 to 8 miles per hour. While if you see this symbol, that is here 61 to 66 miles per hour. And the direction is given by the barb direction. So the barb always points in the direction from which the wind is blowing. For example, if the barb points towards the southeast, it means for this particular location, the wind is blowing from the southeast, and as expected, the air moves out of the regions of higher pressure and into the regions of lower pressure. But if you note, the wind does not cross the isobars at right angles as the pressure gradient force directs. So, this deviation is the result of Earth's rotation and has been named the Coriolis force after the French scientist Gaspard Gustave Coriolis, who first expressed its magnitude quantitatively. The Coriolis effect is the curving of the path of objects or fluids due to the Earth's rotation. And here it is mentioned that all free moving objects, including wind, are deflected to the right of their path of motion in the northern hemisphere and to the left in the southern hemisphere. As we can see, this is the direction of rotation, means the Earth rotates from west to east on its axis, and in the northern hemisphere, if we see, this is the starting direction, but due to Earth's rotation, it is deflected towards the right. Similarly, here also, this is the direction of motion, but because of Earth's rotation, it is deflected towards the right. Similar phenomena is observed for the southern hemisphere also, but here the deflection is towards the left, as we can see in this case also, as well as here also. So, in the Coriolis effect, the deflection is towards the right of their path of motion in the northern hemisphere and to the left of their path of motion in the southern hemisphere. The reason for this deflection can be illustrated by imagining the path of a rocket launched from the North Pole towards a target on the equator. And this rocket would take 1 hour to reach its target. So, if we consider that Earth is not rotating, so after 1 hour, this rocket would reach to the target. But as the Earth is rotating on its axis from west to east, as 360-degree rotation is completed in 24 hours, we can calculate the rotation of Earth in 1 hour. So, the Earth rotates 15 degree each hour. So, if the rocket took an hour to reach its target, Earth would have rotated 15 degree to the east during its flight. So this point was the target, but because of the rotation of the Earth, the rocket reached to this point. So this is the actual destination. So to someone standing on the Earth, it would look as if the rocket deflected off its path and hit the Earth 15 degree west of its target. The true path of the rocket was straight and would appear so to someone out in the space looking down at the Earth. It was the Earth turning under the rocket that gave it its apparent deflection. When we are in the northern hemisphere, the rotation of Earth is in the counterclockwise manner. Thus, the deflection of the object or the fluid is towards the right of the path of motion. But for someone in the southern hemisphere, the rotation of Earth is in the clockwise manner. Thus, here the deflection is towards the left of the path of motion. Thus, the Coriolis effect is the apparent deflection of moving objects caused by the Earth's rotation. And due to this effect, objects are deflected to the right in the northern hemisphere and to the left in the southern hemisphere. Although it is easy to visualize the Coriolis deflection when the motion is from north to south, but it is little difficult to understand how west to east flow would be deflected. So in this figure, the effect of Coriolis force on west to east flow is explained using the winds blowing eastward at four different latitudes: at 0 degree on the equator, 20° north, 40° north, and 60° north. Direction of wind at these four latitude is shown for three time period. This is initial time. Here we have after 4 hours and here after 8 hours. And arrow with dotted line represent weak winds while the solid line arrow is representing the strong winds. And if we notice, after 4 hours, the winds blowing at 20°, 40° and 60° parallels appear to be deflected towards the right of their original path, and amount of deflection at all these latitudes further increases with time. However, when viewed from space, it is apparent that these winds have maintained their original direction. It is the North American continent which changed its orientation as Earth turns on its axis, and this produces the deflection we observe. So, in west to east flow, the magnitude of the deflecting force is dependent on the latitude. As we can see, the amount of deflection is greater at 60° latitude than at 40° latitude, and it is greater than 20°. And there is no deflection observed for the airflow along the equator. So here it is mentioned that it is strongest at the poles. It weakens as we move towards the equator, where it eventually becomes non existent. And the amount of Coriolis deflection increases with the wind speed because faster winds cover a greater distance in comparison to the slower winds for the same time period. So here we have some of the important points related to Coriolis force, which is also known as the deflecting force. So the Coriolis force acts to change the direction of a moving body to the right in the northern hemisphere and to the left in the southern hemisphere. And this deflecting force is always directed at right angles to the direction of airflow. As we can see, this is the direction of motion and the Coriolis force is at right angle. Here, this is the direction of motion and again the Coriolis force is perpendicular to it. Similarly, here also the Coriolis force is perpendicular to the direction of motion. The Coriolis force affects only wind direction, not the wind speed. But it is affected by the wind speed because the stronger the wind, the greater is the deflecting force, and it is strongest at the poles and weakens equatorward, becoming non-existent at the equator. Now coming to third important factor affecting wind, that is friction. So friction is the force generated from the resistance between two surfaces, and this friction acts in direction opposite to the direction of motion, and it slows down the relative movement. Near the surface of the earth, there are many things that interfere with the wind, causing it to slow down and change its direction. So, these factors include trees, mountains, buildings, or even lakes. So, any object on the earth, if it provides resistance to the wind, it plays a very important role in frictional force. And contact of wind with the smooth surfaces result in the lower frictional force in comparison to its contact with the rougher surfaces. The effect of friction is only important near the surface of the earth, and impact of friction on air movement decreases as the altitude increases. In the altitude ranging from 1 to 2 kilometer above the earth's surface, there is no effect of friction on the wind, and within 1 kilometer in the atmosphere from the earth's surface, friction plays a critical role in the wind movement. So this 1 kilometer layer is referred to as boundary layer. Within this boundary layer, Friction acts to slow down wind and changes its direction, which results in chaotic airflow that is known as turbulence. In this video, we discussed about the atmospheric pressure and the forces that govern the wind motion. We understood the concept of pressure gradient force, Coriolis force, and friction. So in next video, we will explore how these forces combine to produce different wind flow pattern that include geostrophic wind, gradient wind, and surface wind. Understanding of this concept is very important because this is the fundamental concept in the atmospheric dynamics. These are the references from where the content of this video have been taken. Majority of the content have been taken from the book The Atmosphere and Introduction to Meteorology, and some of the content have taken from these websites. We will meet soon in the next video. Thank you and best wishes.